Hi guys, welcome back to the channel. In this series, we'll be discussing problems from IMONST and from papers which I have yet to solve. So let's look at this paper 3, which is a sample because of the lack of past years. There's only one actually last year. So let's look at this problem. In this video, we'll be discussing 5 problems from the junior section because after that, there'll be quite a large overlap. Okay, so let's look at problems. Wait, oh my god, I forgot now so far. Okay, so let's look at junior problem 1. Here we can see 4 consecutive prime numbers p larger than q larger than r larger than s satisfy the equation p squared plus q squared plus r squared plus s squared equals to 2020. And what is s? So for those of you who have yet to know the definition of a prime number, it is a number that can only be divided by 1 and itself. So can only be divided by 1 and itself, right? So could you guys list some examples? You guys could write some prime numbers in the comments. I don't know. Okay, so this is the definition. And some examples would be 7, would be 13, 31, and so on. So all these numbers can only be divided by 1 in itself. It cannot be divided by any number smaller than them except for 1. Okay, so let's list out the first few prime numbers. Okay, so we will have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, and so on. You don't need to go too big. I'll show you why in a second. So as you can see here, P is smaller than Q, Q smaller than R smaller than S, right? So if we square all of them, meaning we make P multiply by itself twice, same with Q, R, S, we will have P squared smaller than Q squared, Q squared smaller than R squared smaller than S squared. This inequality will still hold. So let's see, we would have P squared plus Q squared plus R squared plus S squared. This whole thing would be larger than 4p squared, which is the smallest term out of all of these, and this whole thing would be smaller than 4s squared, which is the largest individual term out of all of these. So we would have 4p squared, which is smaller than 2020, which is 2020 is smaller than 4s squared. And we can divide all by 4. We would get, give me a moment, we would get p squared is smaller than 505, which is smaller than s squared. So if we take out the square, we will have p is smaller than root 505, which is around 22.4, and then this is smaller than s. So as we can see here, the maximum value for p would be 19, since 23 alone is bigger than 22.4. So this is p max, and then s, for the minimum value of s, it would be 23. So we would have, this is s min. So let's see how many possible sets we can get. So we would have, if p max is 19, we would have 19, 23, 29, 31. So 19, 23, 29, 31. And then we would have, for the middle set, we will have 17, 19, 23, 29. And then if the s is the minimum, meaning 23, then we would have 23, 19, 17, and 13. So let's kind of add up their squares and we can see which one would be exactly 2020. So maybe you could take out a calculator, I'm not sure, but I'd advise you not to do so, to maybe train your arithmetic skills, I guess. Something like this. Okay, so as I write, let's count. So this one will be 361, this one is 529, so this one add up to be 890, this one is 841, this one is 961, so we have 890 plus 890 plus 1802 would be 2692. So this is not 2020, and then this is like too big. Then for 17, 19, 23, 29, we will have 289, 361, 529, and then 841. So adding all of these up gives us exactly 2020. So since we have found we are a step closer to our answer, we do not need to check this, okay? Because we know it's obviously smaller. And then since we want s, right? S being the largest term out of all of these. So S, the answer for S would be obviously 29. So the answer to problem 1 would be 29. Now let's move on to question 2. Oh, okay. Here it is. Okay, so an integer n fulfills exactly 3 of the following 5 conditions. These are all inequalities. So the first one is 2n larger than 70, n smaller than 100, 3n larger than 25, n over 5 larger or equal to 2, and 5n minus 3 larger than 22. What is n? So looking at all of these without some kind of visual representation would be very perplexing, very confusing. So the best, of course, is to have a visual representation to see what's going on. So here's a bit of notation. Okay, so here we can draw a number line. So the more further to the right, the bigger the number. So as we can see, the biggest number here is 100. So let's put it here. And then if we want to say some number is smaller than 100, so if n is smaller than 100, then we would draw a white circle here, because 100 itself does not fulfill this inequality. Then we can move to the left, something like this. Yeah, move to the left. All these numbers would satisfy n is smaller than 100. And then we would have 2n, which is larger than 70. Dividing both sides by 2, we would get n is larger than 35. So here we would have 35, and then 35 itself does not fulfill, so something like this. And then we would have 3n larger than 25. So dividing both sides by 3, n would be larger than 25 over 3, which is equal to 8 1/3. We can pinpoint it somewhere here. So note that my number line is not drawn to scale. Okay, so somewhere here. And then since n is larger than 8 1/3, something like this. Okay, then we would have n over 5 larger or equal to 2. So we multiply both sides by 5, we will get n is larger or equal n is larger than or equal to 10. And then we will have something here. Okay, since 10 itself, since when n equals to 10, this inequality is fulfilled. So we must draw a black circle here, and then we move to the right, because all the numbers to the right fulfill this condition, right? And then we have 5n minus 3 is larger than 22. So if we add both sides by 3, we will have 5n larger than 25. And if we divide both sides by 5, we would get n is larger than 5. So somewhere here. Then might need to move up here. So something like this. Now we can divide this number line into several regions. So we can do it something like this. Like this. Move down, add a few dotted lines to aid us. So as we can see here, in the region 35 to 100, so how many inequalities are fulfilled? We can see 5 of them. So we can neglect this region as it does not match the requirements of our question. Then from 10 to 35, 4 requirements are fulfilled. As you can see, 1, 2, 3, 4. So here we have 4 requirements fulfilled. So here at the same, we can neglect this region here. Then if we see the region of 8 1/3, between 8 1/3 and 10, we see 1, 2, 3 requirements fulfilled. So this is the place where we need to put our focus on. And then for the region between 5 and 8 1/3, only 2 equations are fulfilled. So no. Okay. So this number, this integer we see here, so is between 8 1/3 and 10. Because if it's 10, if n equals to 10, then 4 conditions will be fulfilled as represented by this black dot. So the only n that we find here, we can draw the number line one more time. So here's 8, 8 1/3, we have 9, and then we have 10, which we can't do here. So the only n that fulfills this question is 9, as we can see here. Okay, so what is n, as they ask here? The answer you should give is n equals to 9. No, actually you should just write 9, okay? So something like that. Yeah, since this is the beginning, don't expect it to be too hard, unsolvable for most people, okay? Then we have problem 3 here. Give me a moment. Need to... Okay, so we see here this guy called Hannes draws a circle and two squares on a paper. The figures intersect at several points. What is the maximum possible number of intersection points among these three figures? Then an intersection point, they have given the definition, so something like this. Then assume the number of intersection points is finite. Why do they add this prerequisite? Because if say you draw your squares like that and then the lines overlap, then there are infinitely many, which we do not want to see in this question since it's finite. Okay. And then if two lines touch each other at a point, this is called the intersection point. Okay, I'll abbreviate it by using IP. And then let's kind of move our squares around. So we have one here, then we have two here. Okay. So our guy Hannes here would draw something like this, and then they intersect at several points. Yes, this is a feasible picture, but this is not the maximum that we can obtain. So let's count how many intersection points are there in this picture. So 1, 2, 3, 4, 5, 6. So there are only 6. Actually, there's way more than that. But so this might look confusing because three figures, how are you going to kind of look at how many intersection points all of them have together? So what I would advise you to do at this point is to look in pairs. Okay, just focus on pairs. Okay, so don't get carried away by the three figures, because it's not to the point where it's still very overwhelming. Because in more harder questions, that they won't just give you three figures, they might give you like 30 figures, 100 figures. No one really knows. So let's kind of see. So to look in pairs, we would have what kinds of pairs do we have in this figure that Hannes has drawn? So we would have this one, so which we have two of them. So let's draw another one. And then the last pair would be this one, right? So we want to see between two squares and between a square and a circle, what is the maximum number of intersection points, as we can see here. So let's kind of take this picture away. Let's kind of just look at a square and a circle first. So something like this. Let me, it's not like decorating, but okay. Wow, this video would be so long. I have no idea why I'm doing this. Okay, so let's look at this square and this circle over here. Then if you see here, we only have two intersection points up till here, also two. But look here. Oh, we have more. And then if we do something like this, then there will be a lot. So this is actually the maximum, as you can see here. And then let's count. So here's 1, 2, 3, 4, 5, 6, 7, 8. So for a square and a circle, the maximum number of intersection points for them would be 8, as shown in this figure. So for this one, for this pair, it will be 8. For this pair, it will also be 8. And then for a square and another square, because it doesn't specify that the square can only be in one dimension and not be able to be rotated. So let me erase these points again. So where's my pen? Okay, so something like this. We would have, let's use two normal squares which are yet to be rotated. So something like this, as you can see here. We can see two intersection points here, and then still two. Yeah, there's only two here, right? But watch what happens when I use a rotated square and then I overlap it with a, then I like cover it over a normal square. So something like this. You can see two intersection points here, right? Okay, still two. You can see, oh, 4. No, this is like 6. Then this is 8. Why 8? Let me show you here. So 1, 2, 3, 4, 5, 6, 7, 8. So this is also 8. So for these two squares, of course, one of them is like rotated. The maximum number of intersection points would be 8. So adding all these up would give us something like 24. And this is actually our answer. And if you still don't believe me, I can make a picture like a visual proof for you. So, but first, let me kind of erase these points. Then, with all three of these intersecting each other, more like overlapping each other, you would kind of be convinced that yes, indeed, this figure has at most 24 intersection points. So let's draw something here. So this is our square. Then I'll circle over it as 8 intersection points. Then having this square over this circle, something like this. So then the intersection points will be very close to each other, but I'll try to point them out as precisely as possible. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So indeed, this is the maximum number of intersection points, as you can see here. So the answer for problem 3 is 24. Now let's go down and look at question 4, problem 4. As you can see here, symbols A, B, C, D, E, F, G, H are assigned different integer values from 1 to 8 such that the number A plus 2B plus 3C plus 4D over E plus 2F plus 3G plus 4H is as large as possible. So determine the value of B plus F. Of course, if we have like something like a fraction, if we want the value of the fraction to be as large as possible, so maybe let's say x and y, x over y, if we want this to be as large as possible, so we would want this one to be maximum and then this one to be minimum. So why is this so? Let me show an example. So if we say 1 over 9 and 9 over 1, obviously 9 over 1, which is equal to 9, is much larger than say 1 over 9, right? So of course this should be obvious to most of you. So we want our A plus 2B plus 3C plus 4D to be maximum. So A, B, C, D should be assigned the other, like kind of the larger 4 numbers over here, as you can see. So A plus 2B plus 3C plus 4D, A, B, C, D should be something like 5, 6, 7, 8. But how are we going to arrange them? We still do not know. Then for E plus 2F plus 3G plus 4H, we want it to be as small as possible. So as you can see here, we will have EFGH to be 1, 2, 3, 4, but in what order, we also do not know. So if we want E 2F plus 3G plus 4H to be of minimum value, then we have 1, 2, 3, 4. Then the arrangement would be, since if we put like 4 here, right? If we put 4 here, then it will be 16. But if we put 1 here, then it will be 4. So this one, of course, we want it to be the minimum. So H can only be 1. And then applying the same principle, so H is 1 here. And then G, applying the same principle, since 1 is out, you can only put G equals to 2, because if we put G equals to 4, this is 12, which is too big for the as large as possible number, right? So G would be 3, F would be 2, and E would be, G would be 2, F would be 3, E would be 4, okay? So we see here our F is 3. And then we want A plus 2B plus 3C plus 4D to be maximum. Then we will want this one to have the largest impact, because this is like multiplied by 4, right? So our D should be put 8. Then since 8 is out of the choices, so C should, using the same principles, would be 7, and then B would be 6, then A would be 5. So we have here F equals to 3, and then B equals to 6. So a quick addition will give us B plus F equals to 9, and this is the answer to problem 4, as you can see here. Now for the final one, so let's look at problem 5 over here. Quite a long question, but this is also the last question of our video. So one day Alina bought 5 biscuits and Betty bought 7 biscuits to school. Their good friend Cheetah forgot to bring any food, so Alina and Betty shared the biscuits equally among the 3 of them. On the next day, Cheetah brought 12 cupcakes, all to be given to Alina and Betty to repay the kindness on the previous day. How many cupcakes should Alina receive if she makes a fair distribution with Betty. So the kind of keyword here is a fair distribution. But let's look at it first, okay? So I'll denote Alina as A, Betty as B, and Cheetah as C. So originally this Alina girl had like 5 cupcakes, so and then this Betty girl would have 7 cupcakes. Cheetah doesn't have any. So 5 plus 7, 12, right? And then if we want to share the biscuits equally among the 3 of them, since they have a surplus, so Alina here, okay, so we have 3 people here, so 12 divided by 3, each person will have 4 cupcakes. And then to have 4 cupcakes, Alina must donate 1 to Cheetah, and then for Betty it will be 3, so it will end up as something like this. Okay, then for the green color, then 1, 2, 3, and then the final one is red. This is from Alina. So for here, the red will be denoting Alina, and then the green will be denoting Betty. Okay. So Alina gave 1 cupcake to Cheetah, and then Betty gave 3 cupcakes. So the next day, Cheetah bought 12 cupcakes to be given to Alina and Betty to repay the kindness. So let's draw 12 cupcakes, no, more like 12 circles here. So the meaning of fair distribution in this context would be like they would receive the respective proportions as they gave Cheetah yesterday. So meaning like since Alina gave 1 cupcake to Cheetah and then like Betty gave 3, so the ratio of cupcakes they should be receiving is 1 to 3 for Alina and Betty, right? So to cut up 12 cupcakes into 1 over 1 to 3, we just cut up like this. So this is Alina's portion, then this one is Betty's portion, something like this, right? Then for Alina, she would receive 12 times 1 out of the 1 plus 3, because 1 unit for Alina and 3 units for Betty. Alina will receive 3 cupcakes, so something like this. I know my video is very lengthy, as you can see here, so I kind of apologize, but because I'm condensing more questions into one video, so this should be expected. And the following videos will be much longer than this, so do not if I also hope you guys can kind of support me, and then I don't know, I might continue making this if I'm free. Now since I'm having some gap months, I guess, so I'm kind of free. Then in the next video we'll be discussing junior 6 to 10. Yeah, something like that. Okay, so see you next video. Bye bye.